Hey guys, it's Mr. C here, and in this video we're going to go ahead and find a couple of things. The first is a basis for the row space of the matrix A that's given here. And then what we'll do is find its column space, and of course there's some verbiage that leads into that part because we have to be careful with a matrix such as this when we're trying to find its column space. Alright, so what you'll notice about this matrix A is that it's not in row echelon form, nor is it in reduced row echelon form, of course. So the first thing you probably want to do here is go ahead and Rref the matrix. So you can do that with your graphing calculator, and I'll go ahead and provide you the entries right now. The top row, give me 1, 0, 1, -2/7. Second row, 0, 1, 1, 4/7. And then last row, 0, 0, 0, 0. Okay. Now that that's done, let's see if we can start chipping away at the basis vectors for the row space of the matrix A. Now, as mentioned in the last video, the basis vectors for the row space of the matrix A are found by using the row vectors corresponding to leading ones. And since we have this matrix in Rref, we can see which rows have the leading ones. You'll see that row 1 has a leading one and row 2 has a leading one. Now row 3 is actually a bunch of zeros, and the deal behind that is that row 3 is a little redundant. It probably is, and actually I will say it is, some sort of linear combination of row 1 and row 2 already. So row 3, -1, 3, 2, and 2, isn't really necessary. It's not a necessary vector to help us form the span of the row vectors for the row space of the matrix A. Alright, so with that said, there are going to be two vectors, two basis vectors for the row space of the matrix A. The first being 1, 0, 1, -2/7, so those are the entries of row 1. And the second will be the entries of row 2, 0, 1, 1, and 4/7. Now, if you were peeking at some of the verbiage leading up to this example, in particular at the bottom of page 1, there's a theorem with a couple of parts. Number 1, it says that the elementary row operations do not change the null space of a matrix. Of course, that doesn't apply in this example. Number 2, though, says elementary row operations do not change the row space of a matrix. However, they could change the column space of a matrix. That actually does apply to this example. In particular, these aren't the only two basis vectors for the row space of the matrix A. Since we're seeing in the Rref version of the matrix that row 1 and row 2 are the minimal vectors needed for the row space, we could actually go back to the matrix A and use row 1 as is before the Rref and row 2 as is before the Rref. So there's another way to express the row space of this matrix A. In other words, these aren't the only two vectors we could use for the basis. We could easily use the vector with entries 1, 4, 5, and 2, and the vector with entries 2, 1, 3, and 0. So basically it says that, you know, if row 1 is a basis vector for the row space in the Rref, then row 1 here is going to be a basis vector as well. And also if row 2 is a basis vector in the Rref version of the matrix A, then you could use the original row 2 as a basis vector. But just do be consistent. If you're going to use the row vectors from the Rref, just make sure you use the rows from this version of the matrix. Don't start mixing things up. That could create some complications. Alright, so that takes us to the last example, where it says care must be taken when finding the column space of a matrix after row operations have occurred, since row operations can alter the column space of the original matrix. There's actually a pretty decent example on page 240 in the text that shows you how row operations can kind of change up the basis vectors, ultimately giving you a different space that's spanned. So to be on the safe side, we apply the following theorem when trying to find the column space of a matrix after putting the matrix through Rref. So it's the same matrix A, and just for reference, let me go ahead and get back on the screen what the Rref version of that is. First row is 1, 0, 1, -2/7. Second row 0, 1, 1, 4/7. And then third row 0, 0, 0, 0. Okay, now for the basis vectors for the column space of the matrix A. Now, even though we might be thinking to use column 1 of the Rref and column 2, which I would agree with you to an extent, since they contain the leading ones. Remember how we arrived at these leading ones? It was through Rref. So there's a good chance that these might not be the actual column vectors that help to generate the column space of the matrix A. But even though they might not be, there is some good information from these entries. So even though this column might not be a basis vector for the column space of the matrix A, it does contain a leading one. And since this column contains a leading one, what we'll do is just kind of link it back to the first column from the matrix A. And that's really the trick to finding the column space vectors or basis vectors after a matrix has been done, or a matrix has been put through Rref. Whatever column has a leading one in it, you just link it back to that column from the original matrix. So column 1 had a leading one, so we'll just use column 1 from the original matrix. So one basis vector is 1, 2, and -1. And then there's one more column that contains a leading one, and that's column 2. So column 2 will just link back to column 2 of the original matrix A, and instead of using 0, 1, 0, we'll use 4, 1, and 3 as the second and final basis vector for the column space of the matrix A. So that's the care that we have to partake in when we're finding the column space of a matrix A after it's gone through Rref. Alright guys, I'll be happy to answer any questions you have in class. Otherwise, thanks for watching all these videos. You guys are awesome, and I look forward to seeing you. Thank you.